네, 제2회 웨비나 시작하겠습니다. 안녕하세요. 반갑습니다. 바쁘신 가운데 제2회 퀀텀 웨비나에 참석해 주셔서 진심으로 감사드립니다. 저는 메가존클라우드 퀀텀 이노베이션 랩의 유닛장 김현영이라고 합니다. 저희를 잘 모르시는 분들을 위해 간단히 소개드리자면 저희는 아마존 브레이킷 그리고 마이크로소프트 애저 퀀텀 등 다양한 양자 클라우드 서비스를 제공하고 있고 양자 기술의 산업 적용을 목표로 연구 및 글로벌 파트너십을 추진하고 있습니다. 이번 웨비나는 키스티와 함께 추진 중인 양자 컴퓨팅 서비스 및 활용체계 구축 사업의 일환으로 마련된 두 번째 세션으로 양자 컴퓨팅을 실제 산업 문제 해결에 적용하기 위한 방법과 사례를 살펴보고자 합니다. 오늘 세션은 약 1시간 동안 진행되고 질문이 있으신 분들께서는 줌 화면 하단에 Q&A 채팅창을 통해서 질문 남겨주시면 Q&A 세션에서 메가존 클라우드의 박현호 매니저님이 정리해서 연사분들께 전달드릴 예정입니다. 오늘 세션은 키프 퀀텀의 걸넛 퓨셀과 유진 올레닉 두 분과 함께 할 예정이고 키프 퀀텀은 산업 현장의 문제를 양자 컴퓨팅 기술로 해결하기 위해 알고리즘을 개발하는 양자 소프트웨어 글로벌 기업으로 최적화, 시뮬레이션 등 실용적인 유스 케이스들을 중심으로 활발한 연구와 협업을 이어가고 있습니다. Hello everyone, thank you for joining us today for the second session of our Quantum Webinar Series. I am Hyunyoung Kim from Megazone Cloud Quantum Innovation Lab. We designed this webinar to highlight how quantum computing is starting to impact industry. And today we are very pleased to have KIPU Quantum with us. KIPU Quantum is the leading quantum software company focused on solving real-world industrial challenges using quantum algorithms. We look forward to learning how KIPU Quantum is tackling industrial problems with practical quantum computing applications. Now I'll hand it over to you, Eugene and Gernot.
Thank you very much, Hyun-Young. Can you see the slides? Okay, great. Thanks to Megazone for inviting us today. It's a pleasure for us, for KIPU Quantum이, to be presenting in front of all of you. And my name is Eugene, and I'm leading the customer team at KIPU Quantum. If we switch to the next slide, then I can quickly cover our company. So we are KIPU Quantum. We are designing and building algorithms and software for quantum computers, for real quantum computers. We focus on delivering usefulness on quantum to the industrial players and to those who want to make quantum a reality in terms of the real applications and real usage. We focus on three main areas when it comes to quantum computing. The first area you see here is quantum optimization. So we are designing and building algorithms and applications for the optimization use cases. The second area is machine learning. So in machine learning, we're also designing and innovating to create algorithms that enhance the existing machine learning workflows and thus gain additional advantage when it comes to industrial applications. And finally, on the verge of AI and quantum, so we're also designing several algorithms and applications to enhance AI with quantum and to also use the power of AI to enhance quantum as well. Since we are one of the leading, if not leading company when it comes to algorithms and software on quantum computers, we have to provide support for all of the major quantum platforms. So you see here some of the logos of companies such as IBM, IonQ, and Pascal, and others. So we have already partnered with them, and our algorithms are designed and optimized for these hardware manufacturers. Not only for those, but as you will see later, we also support many others. So that's covered as well. And when it comes to our experience, you can see some of the logos of world's largest customers. So we've been operating on the market for a few years already, and by now we have completed quite a few commercial projects with some of the world's leading companies and enterprises. That's briefly it about the company, and now I'm going to hand it over to Gernot.
Yeah, good evening and welcome. I'm Gernot Füchsel. I'm the Client Engagement Lead at KIPU Quantum, and I would like to highlight a few challenges that we have in quantum computing, also related to make it accessible to industries. And I will have a look with you on different aspects here. Some of them are related to the ecosystem, some are also more technical. You probably have heard of some of the big promises of quantum computing. Maybe you have heard of the wordings like exponential speed up, exponential scaling, quantum advantage, quantum supremacy. We can solve hard computational problems on quantum computers. Quantum computers are more energy efficient than classical computers for certain problems. And these are the promises that also sets kind of expectations for the application of quantum computing. The problem is that the reality shows us that there is no single demonstration of a quantum computation in real production for real business application to deliver real-time solution on large scales. And with this, I would like to, I will highlight why this currently is and where we are going to be in a couple of years, and what needs to be done from a business side as well as from the technology side. So let us first go through what a quantum computer is and where and why it matters. A quantum computer is a programmable physical quantum system. And that means we do not carry out computation in a logical manner, but we obey and apply quantum laws, the laws of quantum mechanics. A quantum computer consists of a couple of qubits. So these are the smallest, these are quantum bits. These are the smallest, let's say, information units that you have in a quantum computers. The number of them determines the system size that we can treat with them. And they are currently limited in real devices that are offered on the market. The current devices also allow only to operate on quantum systems with a certain number of operations. This is something that's the circuit depth that's related to the circuit depth, and that is related to the program length, so to speak, that I can run on a quantum computer before the information gets lost. And under the hood of quantum computing, there are different technologies, how to realize these qubits, how to connect them, how to carry out operations on them. And the original idea of developing quantum computers was to address mainly quantum systems, to understand or to compute how quantum systems behave. And this is what you find under the hood of, or let's say in this area of quantum chemistry, quantum simulations, because classical computers are not a natural environment to simulate quantum systems. So it can be computationally very demanding, very quickly. Those of you who are more familiar potentially with electronic structure calculations know very well how bad the scaling can be. Beyond that, however, it turned out that quantum computers promise also be interesting and useful for applications in optimization, for instance, for solving combinatorial optimization problems, in quantum machine learning, or solving problems in linear algebra, as well as cryptography. These are more, I highlighted them in gold, are more classical use cases, and they require, and that's very important, they require an encoding to quantum, so that we need to translate the classical problem into something that is more related to a quantum computer. This step is called quantum encoding, and this is something that's very important because it determines how many resources we will be using on a quantum computer and how efficient the quantum computation will be. Now, the question is why currently quantum computers are not used to solve industry problems on large scales. We are currently, let's say, in the area where we see certain breakthroughs, certain usefulness for quantum computing, but this is something that's very narrow. It's quite limited at the moment. And the question is, what businesses and what can the quantum ecosystem do in order to make a business ready for the quantum era that is about to come in a couple of years? And on the one hand side, we have the challenge of the technology itself. We have the quantum computing is difficult to understand. It's based on quantum mechanics. It's quite research heavy. So the communication is a little bit difficult. You will be speaking from a business side with many scientists. The technology itself lacks also of standards. It's not that you have one single technology. Instead, you have many of them. The quantum computers have different advantages and different disadvantages. And also, you cannot easily access this technology. It's not that you can go to the store and then buy a quantum computer and use this like your laptop. The hardware currently has limitations in the number of qubits, the system sizes that we can address, also the program lengths that we can run, as well as not all the software stack is also not fully developed, the whole quantum workflows. This is all in preparation. And in order to drive quantum technology or quantum computing towards a business value, this requires a dialogue with the business. Why? Because the business have the problems, they know where value creation is, they know how much for a particular use case, how much market value is associated to that, and also they know how what they essentially need. So, for instance, businesses are interested not so much in the quantum technology, but they want to make better decisions. They want to solve certain optimization problems, and the technology must deliver that. Risk mitigation, cost reductions, all of this is pressuring, and promising is quantum computing here that it can solve these kind of large computational problems. So these two sides, they need to meet and they need to have a dialogue about what is really needed, what is really wanted. And on the one hand side, we know that quantum computing is useful for certain areas, but we don't know exactly where the business value or where the value creation is going to happen. And this really comes from the business side. And instead of waiting for the day X, you can already prepare. Businesses can already prepare for this era of quantum computing and make themselves ready. For the technology side, it is very important that quantum computing becomes more accessible. And this is also what KIPU Quantum provides here. This access to quantum computing. We have the KIPU Quantum Hub that makes quantum computing deployable for business applications. Central to that is the platform where you find, where we treat the fields optimization, quantum machine learning, quantum AI, and quantum simulations. We have deployed here different areas, for instance, the marketplace that is commercial and non-commercial, where you find different use cases mapped that can run on quantum computers. We also have customized services. That is something we build up with customers together in projects. These are end-to-end solvers for specific use cases, for specific applications relevant for the business. And we're also working on developer toolkits to enable research and innovation teams to build their own quantum products. The KIPU Quantum Hub is connected to different hardware platforms. Here you see, for instance, IBM IonQ, Query, and IQM, and many more about to come. So and this is frequently updated. When there is new hardware out, this will also be connected to the KIPU Quantum Hub. You can really use them. You can use the products that are provided on the platform. You can run the quantum simulations on real quantum computers. You can extract and analyze the results, or this is done for you, depending on what kind of business you're going to. And so this is the way how you can leverage quantum computing or use quantum computing. There are different ways we offer to, let's say, interact on a technical level. On the one hand side, we offer quantum journeys. I will highlight one quantum journey in a couple of in the next slides. Here you can really work closely together with us. You explore your specific use case. For instance, we then test whether it makes sense to move ahead with quantum computing, or is it something that is better to solve on a classical computer. We study the feasibility and also make an assessment on the value for quantum. We build prototypes, specific workflows. We make it really customized for you that it becomes ready for production. And then this is the kind of keep yourself ready, and then you wait, updating the hardware. You can really track when the day is to come. It is that a quantum computer is ready to solve your specific problem. Then there's the KIPU Quantum Hub with this commercial and non-commercial quantum products, end-to-end workflows for very specific applications. So this is the kind of templates that are already existing. And also that allows you an instant tracking of the newest quantum developments, be it in hardware, be it in software. It integrates the newest quantum algorithms as well that we develop. And a third package that is also something that's more for technical people, R&D teams, for instance. You can empower them to build their own quantum products. And they can configure these products, and they use also proprietary material, but they can also extend that. And this is a way, let's say, all of this happens in the KIPU Quantum Hub, and then you can really run quantum computations. So now I would like to highlight a work that we carried out in 2023 with BASF. This was a kind of quantum journey. This is a business use case from optimization. It's an automated laboratory where a robot has essentially the job to carry a certain amount of samples to a water mixer, a photo booth, and a shaker. This is a setup with several thousands of probes or samples that needs to be carried out. So each sample has to stay for a certain amount of time in a water mixer and a shaker and a photo booth. And the question is now, what is the schedule that we need to carry out? The sequence, so to speak, we need to carry out that we complete all tasks in the least amount of time. And actually, this is a problem that can be solved or can be formulated in the Kubo form. This is a quadratic unconstrained binary optimization problem, and that can also be solved on classical computers. The real demand is here that this solution needs to be delivered in real time, because the setup of the manufacturer of the factory will depend, let's say, on this input. And it turns out that indeed you need more compute time than the update of the factory is going to be. And that was the reason why BASF was interested to explore the, let's say, ability of quantum computing to address this specific problem. The computational problem can be formulated in an Ising Hamiltonian. That is something that you see here that can be mapped, and that can also be executed. So like in all customer journeys, when people usually take what they have available, right? So quantum algorithms, and they meet a lot of challenges when they run their first quantum simulations, be it on a classical device or on a quantum computer. So, and these challenges are, first of all, is the quantum algorithm that is used to solve a specific problem. Then when we turn into a real quantum computer, we have a limited amount of physical qubits that restricts us what the system size that we can map on that. We have the qubit connectivity that has a great impact on the circuit depth, the program length that we can essentially execute on a real quantum device. And there's also the intrinsic coherence time that also restricts the execution of the circuit depth. And what we have seen when customers start to explore quantum computing, maybe they take more standard algorithm. In this case, maybe it's a QAOA algorithm, quantum approximate optimization algorithm. And if you solve this specific problem of BASF on a 16-qubit instance, then this is that's the result that you get. A bit string is a specific encoding of a solution. So each bit string corresponds to a specific solution of the optimization problem. And the most optimal bit string, this is highlighted here in purple, and the quantum computer will usually give you many different solutions out, optimal as well as near optimal. So, and what you see, this is an algorithm that just runs on a classical computer. So this is the way how you can check the performance of the quantum algorithm. And what you see here is that the most optimal peak in purple is not very well distinguished from the rest of the peak. And that's the point when you decide to say, no, this does not make sense to really use noisy quantum hardware as it is currently out there. So, and then to spend more time, let's say, on run a real quantum computation on a real quantum computer. And often what we have seen is when people get these, let's say, less useful results out from these quantum, when they are using a quantum algorithm, is that there's a certain customer frustration due to the low performance of common algorithms and hardware when they solve. So they're asking themselves, so what is quantum computing good for if I cannot use, or if I cannot solve even a most trivial problem that I can easily do on a classical computer? And that question is indeed a question that one should ask here, and I will show you what it means in the development of the quantum computing technologies. What we really need are very good quantum algorithms to deal with the shortcomings of quantum computers. And that also means that they produce very short quantum circuits. And this is something that we have offered then to BASF. You see here on the right-hand side a comparison between a KIPU simulation with a KIPU algorithm and the QA-OA simulation that I showed before. And here you see already that the most optimal peak or solution is more distinct in the probability from the rest of the peak. And that's the point when you ask yourself, or can tell yourself, that this makes sense now to run it also on noisy devices. Overall, we have seen that in comparison to QA-OA solutions, we could increase this peak probability by a factor of up to 600, which is really significant, which also says that we need less quantum resources essentially to resolve this particular peak later in a real quantum computation. So this improvements that has just brought this the implementation of a different algorithm here told us that we can run real quantum experiments. But now, if you do that, you are left with the choice of the quantum computer. We have done the same quantum circuit. We executed here once on IBM hardware on 16 qubits. And you see that the most optimal peak, that's the peak that we really want to measure and want to determine, has the lowest probability. But if we do the same thing on IonQ hardware, then we get a very nice peak here, a little bit more than 3%. So why is this? The optimization problem itself is an all-to-all connected problem, and IBM is not an all-to-all connected device. So that means we have to mimic this kind of all-to-all connectivity on a device, and it leads to very long circuit depth. And the result of this is that the solution is very noisy and you lose this information. IonQ, on the other hand side, provides this all-to-all connectivity, and as such, the circuit is much shorter that we can implement there, and therefore also the solution is much, much nicer. Okay, so what has changed from 2023 to 2025? You see here a timeline that's going from 2020 to 2025. With publications that involved scientists also from KIPU, and the number of qubits that are used to solve optimization problem on a real quantum device. And the work that I highlighted here, it's almost happened here around 2023, and in 2024 we moved to 100 qubits, and then by now we are using 156 qubits. So these are developments that necessitated changes in the hardware, that needed changes in the quantum algorithms, and it needed changes in the encoding paradigms that we use. And in the news, in the latest paper on 156, we could already demonstrate that it's possible to achieve runtime quantum advantage to solve an optimization problem. And by 2030, we expect, or some hardware roadmaps point to the appearance of 1,000 logical qubits and 100 million gate operations. That is huge. This will enable to tackle very large optimization problems. And also the program length, essentially the complexity of the problem that is associated to this, will be much, much higher than that we can do now. So by 2030, we expect that the business impact of quantum computing will be dramatic, will be large. And we advise also currently businesses to keep themselves or to make themselves quantum ready. And I already showed you how this is possible. This can be done in different ways. And yeah, well, this is essentially what I wanted to show you. And maybe now Eugene takes over to show you a little bit more about the platform and how these services look like.
Thanks, Gernot, and we can immediately switch to the next page. So far, Gernot talked about our approach and what is currently possible in the quantum computing space and what the perspectives are. And now I will talk about the applications. So we at KIPU Quantum, if you move to the next slide, we at KIPU Quantum, we have already worked on many commercial projects together with customers. And by now we have extensive experience pretty much in every single industry that you can think of. The first example here is a car manufacturer in Europe. Well, the name of the car manufacturer has two letters in its name. And for them, we solved several problems with application of quantum computers. The first use case that we tackled is called vehicle routing problem. So more or less an optimization of routing. And the second use case that we tackled was capacity planning for fleet logistics. The interesting thing about this project is that this was done in 2025, and the interesting thing about this project is that this was done on a real quantum hardware. You can see here IBM mentioned. And when we did this project, there was a request to have this dynamically refreshing. So we are at the point now where we're able to run the use cases not only on real quantum machines, not only on real quantum hardware, and demonstrate the benefits that the quantum computing can bring, but also to have the system refresh and do the continuous recalculation of the optimized routes, for example. So this is something that is, let's say, demonstrating and confirming that very soon we will have these systems moving into production. Let's switch on to the next case. This one is just released maybe a couple of weeks ago. We worked with Komatsu Mitsui. You see here a very large excavator. So they are a heavy machinery company. They produce excavators, cranes, and many other different machines. And they have a specific problem that they invited us to have a look at. It turns out they have several components in these machines that are very expensive, and they break at regular intervals. When I say regular intervals, I mean that the components are breaking, but they don't actually know when the components will break. So in this case, we're talking about very expensive cables that cost more than $100,000 each. The problem is that it's very difficult to understand, to predict when the cable will break. So you more or less have two options. Option one is you replace the cable before it breaks, well before it breaks, and then you're wasting the money because you replace it too early. And option two is you wait until it breaks, and then the whole operation stops, and this produces a significant losses in terms of profit and so on. So basically, the mining production stops when you have such a cable being broken. The company, so Komatsu Mitsui, has already started to use machine learning, but they were not satisfied with the results that they were getting. And this is where they got us involved, and we introduced an additional step, which utilizes the quantum computing. So what we proposed is to enhance the data using quantum calculations and quantum pre-processing before the data is being sent to classical machine learning. So more or less, we are not replacing the classical machine learning. We're complementing by doing the pre-processing and enhancement of the data using real quantum computers. And as a result of this step, with the very clever algorithms that our scientists designed and which are now productized, we were able to demonstrate an improvement in terms of predictability by more than 10%. So this example here is very colorful because it's real. It applies to a real use case scenario. It can be run on today's quantum machines, and you can create useful results that can be moved to production even today. So this is quite impressive because Gernot was just talking about the fact that there is the quantum computers were on a trend and on a path to become useful, but we're still in this era where everything is being prepared, and it's very important to prepare your company for when quantum becomes useful. Whereas here already we can say that yes, you can use this particular problem. You can use quantum computers to solve a real industry problem. Gernot, please move on to the next slide, and I will talk very briefly about some of the other use cases. Here we are talking about a banking use case where regulation needs to be met. There is a specific regulation called Basel III FRTB-SA, which regulates how much capital you need to freeze in order to cover the risk. We worked with a finance customer in order to optimize. So this is a portfolio optimization case. In this particular instance, the target is to reduce the amount of assets that is being frozen, and therefore you can move the unfrozen assets to the investment space and gain interest on the unfrozen assets. So we managed to demonstrate a reduction of at least 10%, which leads to the fact that you can take that 10% freed up assets, move them to investment, gain interest on it. So it's a very quantifiable use case where you can see a direct relationship between what quantum computing was able to do and how much additional revenue this could generate for the bank. Next slide, please. Yes, a very different use case, but also possible, and this is what we're doing currently with the quantum computing. So this one is in machine learning. There is a drone at the oil and gas company in the oil refinery. The drone takes thermal images of the oil pipes. And we worked with the customer to enhance the detection of leaks in these oil pipes by applying quantum-enhanced machine learning. The results that we've been able to observe are 13% plus improvement in terms of accuracy of leak detection. And the interesting thing also about this project is that because the customer sees a direct usefulness of the quantum computing and how it can benefit the accuracy, we are discussing about a multi-year implementation now that will be linked to their production. Next slide, please. I think I will finalize with this case. So we worked with a car parts manufacturer company called Schaeffler on a thermal simulation case where quantum computing was also useful. And you can see here a QR code of customer talking about their quantum journey and how KIPU helped them in this quantum journey in order to get the whole company ramped up and ready to go for the quantum era. This is where I'm going to stop, and now I'm going to talk about how we are delivering such projects and how you can also create your projects without the hassle of setting up the infrastructure and everything else. If Gernot stops sharing the screen, then I can share my screen and I can go directly to the demo. So, can you see my screen? Perfect. Okay, so what you see here is a platform called KIPU Quantum Hub. Gernot already talked about it, so let me go briefly about the key components that Gernot talked about. The first component being the access to the hardware. So the platform itself, very briefly, is a tool that makes quantum accessible for all kinds of audiences and all kinds of users. So if you're a student, you can use this platform right away, register for a trial account and start trying quantum with the emulators. If you're a university, you can create courses, you can create the backbone of your lab for your research. If you're an enterprise company, you can already start creating quantum applications and run these applications here on the platform and connect them to your internal infrastructure and to your own internal applications and workflows. So pretty much for every kind of scenario, this platform can be useful because it covers all of the needs, starting with the hardware. So you can see here various hardware machines. We've basically gone out there and contracted every single large quantum provider, and therefore you get access to the quantum machines here. Besides the real hardware, the real quantum hardware, you also get access to the emulators, simulators, and classical hardware. Why? Because in order to provide this experience of being able to build everything on quantum, you might want to do the simulation or emulation before you move to the real quantum machines for various reasons. And I think I can safely say that there is no application out there that doesn't require the classical resources. So that's why we also provide classical resources here. So that was the base layer, the access to the hardware machines. The second layer is the marketplace. So we talked a lot, especially Gernot covered a lot about the algorithms and our work for customers. So because we are doing a lot of research, we make a lot of this new achievements, new innovation available as packaged algorithms, and you can see some of the algorithms here. They are both in the optimization space as well as in the quantum enhanced machine learning. And you can see that the marketplace actually has not only KIPU produced algorithms and components, but also the components from third parties. So if you wanted to publish your own algorithm, whether for free or commercial, this is also possible here. So this is, let's say, the second step. First step, you take the hardware infrastructure. So we make this accessible. The second step is you need best in class. And Gernot talked about QAOA algorithm, which is commonly available. And you could see there when Gernot talked about it, that the KIPU's algorithms are superior comparing to what is openly available there. So you do need best-in-class algorithms in order to build these cutting-edge, or let's say best-in-class applications for your use cases. You can see here that everything is documented. There is access through the APIs, and it's very easy to plug in these algorithms into your applications. But of course, that's not it, because you might want to build a whole application, and for this scenario, so for this requirement, when you need to build a whole application, we designed a space called use cases here on the platform, and this basically is the quantum visualization. So this is the space where we host quantum applications for our customers and also for the public. The ones you see here are the publicly listed use cases, which means that you can access them even with a free trial account. For the customers and for commercial engagements, they have their own private space where we host the applications that they create or that we created for them. For today's presentation, I'm going to go into the assembly line scheduling. So remember what Gernot talked about, a project in 2023. This led us to productize some of the algorithms, and also this helped us to eventually also create prototypes and products related to the actual use case itself. So not only the algorithm, but actually the visualization. Unlike Gernot's case, so he talked about robots doing the preparation of chemicals. This use case is related to the car manufacturing, and although the use case is different, the actual underlying use case or the underlying algorithms, pretty much everything is exactly the same. It's optimizing the scheduling of your production. In case of cars, you have a problem where you have a bunch of components in the factory. And of course, in order to create a car, you need to put all of these components together. Now, the challenge that often happens in the FMCG industry and also in automotive is that many customers have the ability, or let's say every customer has the ability to create their own car, and therefore it's highly customizable, and this creates kind of a small nightmare for the producer, for the car producer. You have you have all kinds of possibilities in terms of the configuration, and then on one side, on the other side, there is no car that is the same, and this makes production very complex. When you are making this assembly, so for example, there is different body types such as sedan or pickup. Then there is different vehicle features such as the all-wheel drive, there is the auxiliary heating, and maybe some other things, and there is additional options specific to the regions. So of course, when a configuration like this is sent to the factory, one of the biggest challenges is how to make a sequence of the cars so that it takes least amount of time on one side to produce, so therefore you can maximize the output of your production, and on the other side consume less resources and also comply with some of the constraints. For example, we looked here at the top at the different body types. Well, it might be that actually to reconfigure your assembly plant from pickups to the sedan, it takes a couple of days time. So you want to group the configurations that are of the same type, or let's say the same constraint, in one bucket, and then move on to the next one, so that you don't keep changing the setup of your production from every car to every car. And then on top of this, you have some other constraints, such as after you've painted the car, you need to leave it aside for a bit of time before you can start working on it, because the paint needs to polymerize. So all of these constraints plus all of these possibilities in terms of configurations make it extremely complex to come up with an optimal solution, and this is where quantum computers can be useful in the future. And as I mentioned, we worked on this kind of problems already for several commercial customers, because they want to get prepared for the age where quantum computers with enough qubits and with the best-in-class algorithms will be able to optimize their production to the best possible way. For the sake of the demonstration, I've just generated 5 different configurations. Let me try and start the optimization right now in real time. And meanwhile, let's talk about what we see here. So the random generator has produced 5 completely different configurations. They have different body types. They have different options. So here, for example, only the trailer hitch. And for example, this one is a hybrid car that is also at the same time all-wheel drive, and so on. So what you see here is a result of the optimization. Because it's only 5 cars, it's done the optimization pretty quickly. And what you see here is that before the optimization was done, so if you just took a sequence as it was produced, you had 25 violations. So this was over the threshold that the factory has set. And the violations are the things which I talked about. So for example, you have the cars changing body type too frequently, for example, or having to wait too little time for paints to polymerize before you start working on the car. So the threshold on the violations has been before optimization has been too, let's say, overachieved, and therefore not acceptable. And then the optimization algorithm was applied to comply with the threshold for the violations, and therefore you can start moving this optimized schedule into the production. So what you see here and what I demonstrated just now is a practical use case of how you can take the algorithms, the platform, and everything else that KIPU created, plus the expertise, and build a use case that can be already useful to a certain enterprise, a certain company. And one thing that you might be asking is, okay, this is great, but usually the companies already have the manufacturing process. They have their own tools, they have their own products, and so on. So how to make sure that Quantum is not creating a silo, but is integrating into the existing workflows? And this is something that I will demonstrate to you now. Hopefully we have we have a couple of minutes, so I can quickly go over this. So what I'm showing you here is a little bit under the hood of how this, or a similar use case, is being run when you click that optimize button. So let's see if I get to the next page. If not, I can show it straight away. Okay. Yes, it's running. Fantastic. So what you see here is a workflow. This workflow is representing a use case similar to the scheduling case that I just demonstrated. This workflow has been built by a supposedly optimization engineer at the factory who has no idea about quantum. Why? Because here, using the workflow builder, you can drag and drop components, some of which could be existing workflow within the factory, and therefore you don't really need to know quantum in order to apply quantum to your workflows. These steps here are going already real time right now, so they're executing, and you see the components here. This component here, this, and this, they are classical, so they could be existing workflow at the factory. And this component here is the quantum optimization. So as you can see, what is happening is, and Gernot talked about it, in order to use quantum, first you need to encode the problem so that quantum optimization or any kind of quantum calculations can be done. So the encoding and mathematical formulation has already been executed here. And now there are two steps in the process, one of them involving the actual real quantum optimization. And at the same time, the system is also producing the pre-optimized result that can be displayed on the screen. The optimization, so this step is complete and the optimization is still running because it's running on an emulator. It takes a bit more time, it takes a bit longer. And once the optimization has been done, then the result is moved back to the decoder. So before you can move it to your existing workflows, you need to translate the data into the classical so that your existing factory components and workflows can understand this data and make it and get usefulness out of it. And that's why you have this decoding step. And finally, this would be your visualization or your scheduling optimization output that you would be getting, just like you saw on the demonstration of the car production. So basically, what I was trying to show you here is two main key things. First, you don't need a quantum PhD in order to build a quantum application with KIPU Quantum Hub. And secondly, this can be plugged directly into existing company productions, whether it's a bank or a manufacturing or a car producer. Quantum can be plugged into the existing workflows using tools such as KIPU Quantum Hub. That is it on my side, and just a couple of final words. You can get access, so you can subscribe and get access to the KIPU Quantum Hub and get a trial account, especially if you're a student. This is very easy. We will activate the accounts for you. And of course, we would be happy to have a further discussion. We will be happy to take questions, and we're always happy to share more experience, especially when it comes to making quantum industrially relevant and industrially useful. That is it on my side, and big thanks to Megazone folks who invited us to speak today. Gernot, any final words from you?
No, but I look forward to your questions, and thanks a lot to Megazone for this invitation.
Okay, thank you very much for the great presentation. We have received a couple of questions through the chat, and I will go through a few of them. I will speak in Korean, and then we'll translate into the English. 혹시 추가적으로 궁금하신 사항 있으시면은 Q&A 작성해 주시면 좋을 듯 하고요. 우선 그러면은 이제 질문했었던 거 먼저 한국어로 얘기 드리고 영문으로 번역을 해보도록 하겠습니다. 먼저 이제 현재 양자 알고리즘 전문가에 대한 수요는 어떻게 변할 것으로 예측이 되시나요? AI 발전이 이들의 역할을 대체하거나 변화시킬 가능성은 없을까요? 라는 질문이 있었습니다. So the first question is that do you think that the demand for quantum algorithm experts will increase significantly? Wondering if AI can replace the role of quantum algorithm experts.
I think I would say that maybe a little bit, maybe it's less than one would think in the first place. The reason is that you see already to bring quantum usefulness, there are a lot of things that you need to do already more on the classical side. So model building, build all these kind of workflows and so on and so forth. From the engineering side, maybe it will become lesser important the better the hardware becomes. This is a phenomenon that you maybe have also seen in classical computing. So, for instance, 30 years ago, you needed to code very efficiently to make a useful program. And nowadays, I think you don't necessarily need this anymore. So, because the hardware is compensating for a bad programmer. And I believe that such a phenomenon will also continue. The reason why I expect that quantum experts, or the amount of quantum experts or quantum algorithm engineers does not necessarily have to increase dramatically, is that we will see also more standardization. So this will also help to avoid that.
Thank you. Thank you for the answer. And second question is that IBM 초전도체와 아이온큐 이온 트랩 하드웨어에서 동일 문제 실행 시 결과 품질의 차이가 발생한 것을 봤습니다. 하드웨어 연결성이 성공 확률에 미치는 영향과 이를 개선하기 위한 하드웨어 소프트웨어 공동 설계의 중요성은 무엇일까요? So the second question is that running the same problem on IBM superconducting and IonQ trapped ion hardware produce different solution qualities. So the question is, how does the hardware connectivity affect the success probability, and why is hardware software co-design essential for optimization?
So regarding the connectivity that I showed, the example for BASF, it outlines it very nicely. So the problem itself, the mapping is more ideal if you have if you have an all-to-all connected hardware, where all qubits are connected with each other. You don't necessarily need that because you can also mimic this when you build a circuit. The problem is that it adds additional operations in your circuit, and it makes it therefore artificially longer. In an ideal hardware, so if there would be no coherence time associated with this, and we could run infinite long programs, then we would expect the same result essentially. But since it's not the case, so we mapped this on IBM. It led to a circuit that was out of the coherence time of that specific machine. We did the same thing on IonQ. The circuit was much shorter because the connectivity was already there, and therefore we got a better result. So regarding the question, how important is the success probability, the probability that's associated to a particular bit string, it is very important. In optimization, we just need to measure. So we run a circuit, we implement a circuit, we run it on a quantum device, we measure, and we measure one of the possible events, right? So if we have n qubits, we have 2 to the power of n potential solutions, and we need to measure. So if the success probability is very high, we can reduce significantly the amount of measurements that we need to carry out on a quantum device. And that means we are much more resource efficient. Therefore, it's very crucial to have very good quantum algorithms. On the one hand side, it decides whether you can tackle a problem on a quantum computer, because you can generate maybe short circuits, and the quality of the results, and the money essentially that you need to spend on a quantum computer. So what was the third question? I think there was a third question associated.
I think it is the good for the answer. Okay, so we're going to have a final question due to the time. 마지막으로 시간 관계상 마지막 질문 하나 하고선 마무리하도록 하겠습니다. AI 기술이 겪었던 것처럼 양자 컴퓨팅의 겨울이 온다고 하면은 이에 대해서 어떻게 대응해야 한다고 보시나요? So the last question is this, how will us and you deal with the quantum winter phenomenon like AI experienced before? So we haven't experienced the quantum winter right now, but what if in the future? Then how can we deal with it, and how can we solve that winter?
The quantum winter, how we can essentially deal with this. Well, I'm not sure what to understand under the term quantum winter. I think quantum computing has a big challenge. It needs to demonstrate business value. And that's a challenge that it had since it emerged, right? So since there were several hypes around quantum computing. And so far, it could not demonstrate a real business value, a real implementation. I am very optimistic what concerns quantum computing, because I work very close here with the quantum algorithm engineers. We are working very close with the hardware vendors, and there are big moves. There's a lot of motion in this ecosystem, and sometimes these are very disruptive. So it's happening something at the moment. We see, for instance, great progress in the field of quantum machine learning. So the point is with quantum computing is that small qualitative changes in the hardware and in the algorithms can lead to big quantitative changes in the application. So, and one should not underestimate how quick this can go. So it's very surprising. That's also what you have seen, or what I tried to highlight, from 2023 to 2025. These are 2 years, and we moved from 16 qubits to 156 qubits. In a couple of years, we will have thousands of physical qubits available and probably 1,000 logical qubits. This will bring a huge change. So I am very optimistic for the next couple of years.
Okay, thank you for the insightful answers. So, okay, I'll hand back to the Hyunyo for the closing of our webinar. Thank you very much.
Okay, thank you, Hyunwoo, Gernot, and Eugene. Thank you very much for taking the time to share such valuable insights with us today. It was a fascinating session. And since it's still morning in Germany, we wish you a wonderful day ahead. Okay, I
Thank you very
share.
much.
Thank you. 감사합니다.
오늘 웨비나에 참석해 주신 모든 분들께 진심으로 감사드리고 웨비나 내용이 유익했기를 바랍니다. 화면에 보이는 QR코드를 통해서 간단한 설문조사에 참여해 주시면 더 나은 웨비나를 준비하는 데 도움이 됩니다. 다음 웨비나는 저희가 4월에 진행할 예정이고 이번 1회, 2회 웨비나에 등록해 주신 분들과 설문조사를 진행해 주신 분들께 웨비나 초청장을 보내드릴 예정이니까 계속 관심과 참여를 부탁드립니다. 감사합니다. Thank you all for joining us today. We hope you found the session helpful. Please scan the QR code on the screen to complete a short survey. Your feedback is important for making our webinars even better. Thank you again and have a great day.